Hello and welcome to this new video. We shall finish section 0.3 actually by talking lastly about distributions related to the normal distribution. Okay. So in the previous video, we learned how to generate a positive normal distribution by using the acceptance rejection method. But if you can do that, actually, we can generate a standard normal distribution. Okay, the algorithm is very easy. Flip a fair coin and let y be the positive standard normal distribution. Okay. If head appears, take x equal y. If tail appears, take x equal minus y. So x equal y with probability 1/2 and x equal minus y with probability 1/2 as well. So actually, it's not difficult to show that capital X actually is a standard normal. Okay, you just do that as an exercise. Okay, and therefore we have the following algorithm to generate a normal distribution. First, generate a positive normal distribution y, then generate a uniform random variable u, and takes x equal y. If u is bigger than 0.5, take x. Replace x by minus x. So it's just another way of saying if u is less than 0.5, take x equal y. If u is bigger than 0.5, take x equal minus y. So you can write this as in a different way. So just the same thing actually. And that's it. So of course, now in the exercise, you will have to implement that. But let me mention actually that because the normal random variable is very, very important, there are other algorithms to generate them or generate samples from them. So here's one of them. It's called the Box-Muller algorithm. It's described in the book of Sheldon Ross. Actually, we generate two normal random variables at the same time. Okay, by taking two uniformly distributed. First, we generate two uniformly random numbers, u1 and u2, and then we take the first variable to be radical of minus 2 ln u1 times cosine 2 pi u2. Okay, and take y to be the same thing but with sine. Okay, I'm not going to prove that actually. See the proof in the book of Ross. But you'll have to implement that. Okay, so this is another method that you should know to generate the standard normal actually. And as an exercise, you'll have to implement the two algorithms and compare their time efficiency. Okay, now if we have a normal random variable with arbitrary mean and variance, it's not difficult actually to reduce the case to the standard normal, because if z is a standard normal, so it's mean 0 and variance 1, then mu plus sigma z is a normal random variable with mean mu and variance sigma squared. It's not difficult. I hope that you know that. It's not difficult to prove at least. So we have now two algorithms to generate normal random variables from uniform random variables. Okay. And now I will state three distributions related to the normal, which are very important in actuarial sciences. The chi-square distribution with n degrees of freedom. We have two equivalent ways to define this chi-square distribution. The first definition is that a chi-square distribution is the sum of the square of independent standard normal distribution. So if Z1, Z2, Zn are independent standard normal, raise each one to the square and take the sum, then you have a chi-square distribution with n degrees of freedom. Okay, so maybe this is the definition that you know. And it follows that, okay, but I have to, there's another way of characterizing it that not all people know actually. There is a formula for the PDF of a chi-squared, and it's given by this formula. It's a constant, you don't need to worry about it. Constant times a power of x times an exponential. And if you recall the gamma distribution from the previous slide, you will notice that this is what actually, this is a particular case of a gamma. It's the gamma n half 1/2 distribution. Okay, so the lambda is 1/2, the alpha is n over 2, or the beta equal 2 if you like. Okay, so the chi-square distribution actually is a gamma with parameters n over 2, 1 over 2. Okay, and therefore we have two algorithms now to generate a chi-square distribution. One by generating normal random variables and taking their squares and do the summation, and one by generating samples from a gamma distribution with parameters n over 2 and 1/2. And we know how to do that. We learned how to do that in a previous, actually we didn't learn, but I asked you to do an exercise as a paper exercise to write an algorithm that generates a gamma distribution. Okay, so you'll have a lot of work to do actually, and I leave you with 3 exercises actually, or just 2 exercises now. The F distribution and the T distribution, which are related to the normal. The F distribution with parameters m and n is by definition what? It's the ratio of a chi-square distribution of m degrees of freedom over its degrees of freedom divided by another chi-square but with n degrees of freedom. Okay, which are independent, of course. Okay, so I want you to write an algorithm for generating an F distribution, okay, and to implement it. And once again, all these functions are actually, all these distributions are implemented in NumPy and SciPy, okay? But I want you to learn the algorithms by implementing it, okay? And the last distribution related to the normal is known as the T distribution or student's distribution or student's T distribution, same thing, with n degrees of freedom. Actually, it's what? It's the ratio of a standard normal over the radical of a chi-squared random variable divided by its degrees of freedom. Okay, this is known as the T distribution. And actually, we have a formula for the PDF of the T distribution. It's given actually by this formula. And you should know that the T distribution, actually, the shape of the T distribution is very close to the shape of the normal distribution, but the T distribution has fatter tails, so it decreases to 0 slower than the exponential, than the normal. Okay, because we have a decay to 0 is a polynomial decay to 0, whereas in the exponential, well, in the normal, you have an exponential decay, and the exponential always wins the race. Okay. Now, but when n is great, actually, when n is big, the two distributions are very close together. Okay. So once again, this is just a constant to ensure that the integral is 1. Okay. So when n is small, actually, sometimes we prefer to use the T distribution rather than the normal approximation. Okay. And yeah, and I will finish this video by giving you 2 references. There are many other distributions actually that you may encounter. I just took the most important. So a complete list of distributions is given in Wikipedia. Just click the link here. And all these are implemented in Python. So there are built-in functions actually in the SciPy library and in NumPy as well. So you can just also click the link here to learn more about them. Okay, So this concludes the video and section 0.3. Okay, so thank you for your attention and see you in the next video.